on our poster, we present basically also my last publication combining static analysis error traces with dynamic symbolic execution. This is joint work with Pritam Garat, Christian Kadar, and Alistair Donaldson. So we have a project page on our group's homepage. You can download the paper, you can download the artifact, you can even the talk from Easter this year. You can watch if you are interested in it. So what's a high-level idea? On the one hand, you have static analysis tools, right? They over-approximate, and typically they give a lot of false positives that can be really annoying, as Jan confirmed in this talk. And on the other side, you have symbolic execution tools, right? But they typically get lost in the vast number of program paths, which is also annoying. So what we do know is we take the error traces from static analyzers and try to confirm them with a symbolic execution engine. And then when we confirm the true positive, or find a true positive, we have a concrete test case for the developer, so we can debug his program. More precisely, we took two static analyzers, Clang static analyzer. Both of them generate traces, not just an error location. You get a trace where you have to go. But a trace, instrument a program, compile it to bitcode, and run it with a modified version of KLEE. The biggest modification here is that we have a targeted search heuristic. So how does it look like? You don't have to read the source code. We have take it for granted that we have a buggy program here with a use after free error in line 23. We run that one through Clang static analyzer, and you get a nice trace. You can watch it in browser. And what it basically says is, in line 10, we have to allocate memory. Then in the next step, you have to enter the while loop. The condition has to be true. In step 3, 4, and 5, you have to take the true branch of the if statements. In step 6, you have to free the memory. In between, we created an alias in 16, so it doesn't work. I don't care. Basically, we created an alias for the original pointer where we allocated memory. And then in step 7, we have to iterate the loop one more time. And in step 8, we have to leave the loop to hit a use after free bug in line 23. That's a step 9. That's what the trace says. So what we do now is we take the original program, we take such a trace, and we instrument the code. You see there's method codes now in that code. And with those method code or annotated functions, whatever you call it, instrumented code, we can internally in KLEE check for every program path, what is the order of steps we take, what are the conditions, are they true or false, right? And there's another feature we can use those, or another property of those instrumented lines, we can actually target them. You know where we have to go in KLEE, right? So we wrote a targeted search heuristic. It works on an interprocedural control flow graph. So let's say we have that graph, there are 3 steps. So, step 3 is the error location. And those small atoms are states that are currently exploring the program. So what we do now is we basically prioritize states that are close or that have already explored the highest number of trace steps. And among those, the ones that are close to the or closest to the next step. What we also do is we terminate here with a Grim Reaper all states that cannot reach the error location, but we keep states that just skip a step. So in initial experiments that showed to be actually beneficial. So no further results. That was for us the surprising part, to be honest. We did our fancy targeted search heuristic. We followed all those paths, but what turned out is that we cannot find all the bugs. So then the first intuition was, okay, then we are being less strict about the conditions we get, like the if statements and the why. We say, okay, we only add it to the path constraints if it actually holds, for instance. And with this relaxed strategy, we find basically all the bugs. And then we were wondering, okay, what if we just completely ignore all the intermediate steps of our trace, what we thought was beneficial, and just target the error location? And it turned out, like where the finger is pointing, that this is exactly as efficient as the other ones, the fancy ones. So that's why there's an experience paper, because that is kind of counterintuitive. We think that you can follow a trace and it gives better results, but it just targeting the error location with the targeted search heuristic in symbolic execution works as well. So that's what one poster is about. Thank you very much.